Hey, good afternoon, everybody. This is Chris Stahelski. I am at Eastern Region Headquarters. I'm the Climate Services Program Manager here, an Observations Program Manager, and we are going to have our latest in the series of webinars for you this afternoon. We do apologize to make sure that everyone had to come to the new link because we had some problems with the one yesterday when we tried to test it. But yeah, this is the recap of the 2022-2023 snow season. So I'll have 3 speakers today lined up for you. The first speaker today is going to be Dr. Dave Robinson. He's at Rutgers University in New Jersey. He also is the New Jersey State Climatologist. Dr. David A. Robinson is a distinguished professor of geography at Rutgers University and New Jersey State Climatologist. He has particular interest in global snow cover dynamics, interactions of snow cover with other climate elements and polar climates. Also interest in applied regional climate and climate change issues. As state climatologist, he works with a wide array of user communities who require climatological information and expertise to solve problems. Dave has been a member of the National Academy of Sciences Board on Atmospheric Sciences and Climate, is a past president of the American Association of State Climatologists, has received the Lifetime Achievement Award of the American Association of Geographers, and is a fellow of the American Meteorological Society. Dave's presentation will provide an overview on snowfall and snow cover conditions across the nation during the most recent snow season. This will include a recap of notable snowfall episodes and anomalies, the latter on both the positive and negative sides of the ledger. The distribution of snow cover and anomalies of cover compared to the 50+ years of satellite era will also be recapped. And I want to say Dave is probably the second person I'll refer to as Dr. Snow after Dr. Uccellini, because literally the two of them could probably confine themselves to a room and talk about snow for hours on end.
And we have. And Louis and I have.
Yeah, but I just want to let you know, I do nickname you Dr. Snow, because I never probably told you that before. But you're one of the two that have that title in my opinion. So Dave, I will be happy to pass the baton for you. By the way, for those of you that may recognize Dave's name, he typically does do this column for Weatherwise magazine. You have to pay to get it. You can get it through the AMS or NWA if you're a member, or just subscribe to their thing. And you have to pay for it. But this will come out, he said, in the November-December issue. So later this year, you're kind of getting an early preview of that today. So Dave, take it away.
Thanks, Chris and Jenna. Yeah, that and more. As I make this presentation today, but this photo taken by the Nevada State Climatologist is going to be part of that issue. But thank you for inviting me to present today. And I'm going to just introduce briefly our global snow lab at Rutgers. We're primarily concentrating on snow cover. With that, we have a climate data record that we provide on a monthly basis, weekly data to NCEI and National Snow and Ice Data Center. So we've been doing that for many decades now, and it's based off of NOAA, National Ice Center snow maps. So I had many years of cooperative work and support in some cases from NOAA. So a big thumbs up to our partners at NOAA. Why is snow important to understand? I got to remind you here in the middle of summer, but whether we're talking snowfall or snow cover here, the fact that it's a water reservoir, and we'll hear more about that later, absolutely. It influences weather and climate. It can be influenced, obviously, by weather and climate. It can certainly be dangerous, as we see all too often during the snow season, be it avalanches or road hazards and such. Very important for wildlife, both in a positive and negative sense. And yeah, it's a heck of a lot of fun to play in. Now, of course, when the snow is so deep that your lifts can't operate, you got a little bit of a problem there. This is a fun question I just always throw out in my general talks. Did it snow because it's cold, or is it cold because it snowed? And of course, we all know the answer is yes. So just keep that in mind. There is that interaction with snow in the climate system, whether it's being snowfall or snow cover. We'll see an example of that towards the end of this brief presentation. First, we're going to look at snowfall with our recap for the season, and then look at snow cover at the tail end. And you can see a very heavy, wet snowfall there. Yes, that's New Jersey, but it certainly wasn't this past winter in New Jersey. Annual snowfall, I don't think I need to tell any of you folks the general distribution of that snowfall. And you can see the mountains, the lake effect, those are the areas with the heaviest snowfall. That's a climatological look at things. This is a map put out NORISC at the Operational Hydrological group out in Chanhassen, Minnesota, cobbled this together. This is snow accumulation for the last season, essentially. Very little fell before October 1st. And you can see it follows the general pattern of what we saw in the climatology, but there are a few areas that kind of stand out as being a little ample this past winter, and that would be the northern plains in particular. It's very difficult to tell that there was deficiencies here in this traditionally climatologically less snowy area. And of course, it's difficult to pick out just how enormous the snowfall was in the Sierras and other parts of the western mountainous and intermountain region. But interesting that the whole distribution, and this will be a theme behind this quick presentation, is kind of a warm, snowless east and a cooler than normal, snow-filled west. And there you can see it for the winter season. But let's recap some of the storms that came along, some of the notable storms during the season. Really started off with two big lake effect events. Buffalo got the lion's share of the attention there, but you can see up on the Tug Hill Plateau of New York, but also notice the Upper Peninsula of Michigan and even the eastern shore of Lake Michigan in the state of Michigan. And this was the major event in November, and then the very noteworthy and tragic event that unfolded just the days before Christmas in the Buffalo region. But notice how relatively small the area is. Even for lake effect in the east, there was a very small area that got hammered, but that area was certainly hammered. And we'll see evidence of that later with some of the winter statistics. This just shows you two more shots you're going to see from WeatherWise taken off the shores of Erie in November, and then by a National Weather Service at the Weather Service office with the incredible heavy wind and snow of the pre-holiday event. Now I'm going to take you on, I call it a trek rather than a track, but this was the general trek of systems during the winter. The WeatherWise article is going to be entitled Haves and Have-Nots, because that was an appropriate look this winter. And you can see here, it's snowing in the Sierras. It spreads the next day in December here out into the Intermountain, then makes it into the Rockies and begins to spill out onto the plains, and then heads up into western Nebraska, northern Nebraska, the Dakotas, over into Minnesota and northern Wisconsin, the upper P of Michigan. Hung on there for a day or two, a little bit spread into the far northeast, and they got a good covering of snow upstate New York, the Adirondacks, into central New England, and then eventually up into northern New England out to sea. This is the general pattern. We see many a winter, but this general trek or track was seen quite commonly, and why we ended up with very heavy totals compared to normal up in the northern plains by winter's end. This is a rare one for the winter, a kind of, I call it a southern-ish because it didn't actually track through the southeast, but it came out of the lower Rockies, southern Rockies, across up into Michigan, and then hopped over into northern New England. An unusual track for this winter, but one worth mentioning nonetheless, because after that, as we'll see later, you had the greatest coverage of snow over the lower 48 after this event. 60% of the lower 48 was snow covered following this event. And that was the high for the winter season. And here I picked this one out, a little different product out of No Risk, simply because it struck me how quickly that storm, again, another Northern Plains, upper Midwest storm, how quickly it moved over the course of a 24-hour period. So this is a very fast track storm here in late February. And then I call this a bookend event. Sure enough, still snowing out in Sierras, Northern Rockies and such. But the real hit at this point was in northern New York and central New England, where upwards of 4 feet of snow fell in the lower Green Mountains of Vermont and some of the northern Catskills and southeastern Adirondacks. They really got clobbered with this storm. Certainly the hallmark storm of the winter, as spring was on the doorstep there. And then finally, we call it the last hurrah. Mount Washington, the summit of Mount Washington had, I think it was 4.7 inches of snow on the 7th into the 8th of June. Kind of heavy snow even for them at that time of the year. And that was the last multi-inch snowfall we found in the lower 48 and even Alaska at reporting stations in Alaska for the winter, or should I say the snow season of 2022-2023. Here are some totals. This chart, this is the first part of the chart that will appear in Weatherwise. Notice Marquette well above normal, the Northern Plains, Duluth well above normal, Bismarck well above, Minneapolis well above, even out in Andrew's country of Salt Lake City above. Sure, Buffalo's in there with more than their average, but look at the southern shore of Lake Ontario. Rochester had less than half of their average snowfall, as did Syracuse. So it wasn't a big lake effect snow season unless you lived in Buffalo and maybe up in Watertown off to the northeast of Ontario. And then you can look down here, and that's on the high end. This is on the low end. And this is where tears fill my eyes, because 2.3 inches of snow in Central Park was common for central New Jersey too, where I am. One of the lowest snowfall totals at Central Park. It was the lowest snowfall total going back to 1869 or 1870. So a real snow drought in the mid-Atlantic and down towards the southeast and lower plains. And you can see in the middle line there, from Kansas City up to Chicago and then north of Milwaukee and all, was kind of like the average zone, if you will. Areas to the north had more, to the south less than average. Now quickly, some snow cover. This is what I find the best use of a golf course end of snow cover is to get out my cross-country skis. This is a product we produce for the World Meteorological Organization. We just submitted our annual report to the cryospheric group there. The purple line was Northern Hemispheric continental snow cover extent for the past 12 months. The dotted line is the 56-year mean from satellites. And then the lowest period of record, not lowest year, the lowest period of snow cover we can find at that particular time of the year over the 56 years is the orange line, the heaviest the blue. Notice in November, the hemispheric snow cover was at a record extent, but it quickly settled into average and then ran somewhat below average for the rest of the season, particularly melting out quickly, as is wont to do in the last decade or two, in particular in May and June. But looking back to the lower 48, this is that January 26th period I mentioned before, where that southern track storm came in and the most snow coverage of the season in the lower 48. And I kind of guessed here for the late February, where I thought perhaps SWE, snow water equivalent, was at its high for the season here in the Northern Plains parts of the Northeast, and wasn't quite there yet in the West, but was getting there. So there's no statistics on when SWE hit its maximum for the season, but certainly after the spatial coverage did. Here is what the NOAA IMS snow map looked like for the 26th of January. And here's our course. We're coming up with a higher resolution product soon. The areas in blue had above normal snow coverage on that particular day. So again, demonstrating it was the max for the season. This is our new higher resolution 24-kilometer departure map for February, which very neatly shows you the snow drought here in the east and the snow surplus in parts of the west. And it ties in with February temperature anomalies as well, both the anomalies and the rankings. Now we're going to turn quickly, finish up with looking at North America in May. And this was the average extent we computed for May snow cover in percent cover. But you might say, well, is that usual, unusual? Well, this tells you that there was a negative departure. The snow melted very early over Canada in May. And it was a record low snow extent for North America in May. And you might say, that's interesting. It was warm, snow melted, lower albedo, warmed up further, dried things out. What came next? Well, here's the temperature departure for May, both really zeroed in from a global map. And here are some numbers out of Canada. These are in degrees Celsius here, 5, 6, 7 degree positive anomalies. So melted the snow melted, it helped to raise the temperatures, helped dry things out. I don't think it's necessarily a coincidence, but how about the consequences? And there you go with your wildfires in Canada in the month of May into June and as we talk. And there's the consequences in northern New Jersey on the 7th of June, where street lights were on in the middle of the day due to the influx of smoke from, at that point, Eastern Canadian fires. Finally, just a couple last images. The future of snow. Is there a future for snow? Will I be invited back in future years to talk about this? Well, this is something that Brian Benschneider does wonderful work putting these maps together. He's up in Alaska, and he looked at normals for snow from the current 30-year normal versus the previous 30-year normal, and saw a decline in snow along the southern boundary of where we normally experience snow in the winter, but a surplus up to the north. Now, yes, we saw that basically last winter east of the Rockies. We certainly didn't see it west of the Rockies, but I'm not saying that last winter's snowfall was dictated by climate change per se, but it's indicative of what we're starting to see in terms of trends in snowfall as we go in zones from south to north across the lower 48. And finally, yes, I found this snowman world, that was this winter, but not in New Jersey. We had to go to, literally, I'm at the Arctic Circle here in Rovaniemi, Finland, over the holiday season, finding snow and skiing and such. So couldn't pass up snowman world. And with that, I will stop my slides
and they provide climate data services for all of California. He also manages the state's atmospheric river research program, which is definitely an important program for water out here in the West. So today, Mike's going to present an overview of how the wet season, which is roughly October through March in that area of the country, how that played out in California, pivoting from the extreme dry conditions to extreme wet conditions. And he'll share some expectations versus outcomes, and then how the snow melt season played out and how it sets the stage for what we may see in 2024. So Mike, Oh, by the way, folks, if you'll hold your questions to the end for all three of our speakers, and you can type them into the chat at any time. But without further ado, I will send it over to Mike. Please take it away.
All right. Hello, everybody. Welcome from California. Yeah, this was a really interesting year. Let's see, try and get that out of the way. All right, there we go. So this talk will start with the antecedent conditions, understanding that 20, 21, and 22, the water years, which go from October 1 to September 30, were the driest 3-year stretch in our observed record, beating out 2013, 14, and 15. So we're seemingly doing a good job of getting record-setting multi-year droughts here of late. And then how suddenly things changed very much. And then went an entirely different direction, particularly related to snow. So we'll hit the highlights of the season and then talk about that, how we observe things, the models and the expectations, and where that sets us up as we head into the next water year. All righty, so let's see if we can get here. There we go. So just to kind of help you get a sense of how we do things here in California, our wet season starts generally in October. Fall precip onset tends to happen around October 1 up near Crescent City at the northern border. It takes all the way to Halloween for that onset to set in San Diego. So that's on average. So October, November, that's when we see the fall rains start and our wet season begin. Really important the timing of that relative to the calendar as whether or not it falls as rain or snow. Snow setting up on a dry soil from a dry summer tends to mute the spring runoff. So really understanding that helps you set the stage for what's going to happen. We get into winter, December, January, February. On average, half our annual precip shows up in this 90-day window and can be wet or dry with notable anomalies, or as we've seen, you can cycle through them through this time period, leading to some really interesting outcomes. Spring, March, April, May, we really have, this is the late season. Precip starts to fall back, usually ends sometime in May, and we won't see it again until October unless we get some odd decaying tropicals. But if winter's a bust, sometimes we get a hefty spring, a late season bailout. Sometimes we get an early shutoff and you don't get anything. Peak snowpack happens around this time, and we pivot in our water management from kind of flood management into water supply, particularly for multipurpose reservoirs. In summer, we really look to how fast things dry out and how strong. Any of those heat events, it's really no matter of if, but when, how big, and how long. And then we're starting to see some interesting things happen as the West Coast gets to deal with some tropical activity. It used to be a fairly rare event, but it's becoming more episodic, and that'll be really kind of interesting to see how that plays out. One of the things we talk about in water management is, and usually this starts happening by around April 1. Well, this year was this way. What about next year? So the idea of multi-year prediction, big deal in the water management community, even though it's hard enough just to get a 90-day outlook in place. So just the expectations we deal with here, and then really beginning to understand how much different will the next decade be relative to the previous one, because we've recently experienced some decades that are notably different from each other. So put this together to kind of describe this last decade of it, which has been a lot of extremes. So really took the historical record for precip temperature and snowpack and did percentile rankings and said, well, hey, 40 to 60%, that's our expected zone. All our systems are built for this. And as you see over the past decade, really only landed 1 year for precip and snowpack in that area. You'll notice temperature didn't bother to fall into that region at all. Have the anomalous region, and this region is where, there's some adjustment to be had, but really could be navigated with some minor modifications. And we have the extremes where really you might have to play to a different playbook. And you can see from the graphic just how much of time we've spent in that area, both in the dry and the wet, but predominantly dry. So then let's build our water year this year. Well, we start slowly. We kind of have a muted start as we get into December. Now remember, we're almost a quarter of the way through the water year. First of our big three in the books, and we're at Christmas, and we only had about 20% of average precip for the state. So pretty well thinking, oh, year 4 of a record-setting drought. This is going to be awesome. Then something happened. We had almost winter in a 3-week period. So we go from one of our driest runs into one of our wettest windows. In that area marked by B, a 3-week window where we saw 46% of our annual precip show up across the state and 86% of our snowpack develop. We then took a month off, thankfully, because we had some floods to record, a lot of damage. Kind of get organized a bit before the next wave of storms starts. Now I put C in a different color because this was a really different type of storm. January storms, classic atmospheric rivers, which was actually helpful in the forecasting of them. The ones at the end of February were a different animal because they were cut-off lows dropping out of the Gulf of Alaska, but then they interacted with some significant moisture, leading to some really unique snow accumulation, including places that don't normally see snow, leading to snow emergencies in places where communities were actually buried that aren't used to having snow in the first place. We didn't stop there because then we decided in March, let's throw in a few more atmospheric rivers, throw in some peak flows, and with those 2 sets of storms, we reestablished the Tulare Lake bed. So you see some stats there for the wet season, statewide 6th wettest at 153%. For the San Joaquin Climate Division, the wettest. And it's only the 4th year since 1950 that we cleared 200% of average for snowpack. We'll get some graphics on those. So here are the atmospheric river footprint for through March of 2023. And we see the exceptional one kicking things off on December 27th, just after Christmas. This is the beginning of a 3-week stretch with 9 atmospheric rivers, 3 of which were strong. And that's notable because in 2020 and 2021, we only had 3 in that 2-year span. So then to get 3 of them plus a whole bunch more in a 3-week period really created a lot of consequence. And you see they're really clustered there. And I'll show you another map that shows how that footprint shows up in the precip mapping. And here it is. So you see December 1st, 2022, things are looking pretty grim, particularly in our water supply areas in the northern part of the state. Remember, this is would be year 4 of a drought, and it's already the previous 3 were record-setting in terms of their dryness. Christmas was looking pretty harsh, but then things changed, and you see by the end of April an entirely different footprint, but you really see the heavy footprint from the Bay Area to San Diego. The big areas in the north didn't fare badly. 120, 140 is not a bad thing to experience, but it did leave us with one of our major reservoirs, Trinity Reservoir, up in the Klamath system, but a key component of the Central Valley Project for the Bureau of Reclamation, and only about half of average storage. We did not get all the recovery everywhere. So you have this situation where you're responding to flood emergencies, but you have lingering drought impacts, a really complex response environment, and a really complex communication environment to help people through everything that's happening. So here we are, here's the statewide April 1 snowpacks, and you see the previous 3 big years there, 1952, 1969, 1983. Kind of episodic, but then we went 40 years and we didn't see it until now. So it's not that it can't happen anymore, but when it does, it's really a bit of a shocker. The last time the Tulare Lake bed also formed to the extent it did was 1983. So then again, it's kind of a generational thing at this point. You don't have a lot of people who are working back in 83 to know how to respond in this kind of environment. Snowpack wise, take a look. These are our regional snow plots, and these are based on our automated sensors. So they only go back to the early 80s, meaning we only capture 82, 83 as that biggest pack in this period of record. And we can see this year relative to it. In the north, it didn't match up. It really a little bit bigger than 18, 19, but really not quite as extreme as it was. And as you can see in the Southern Sierra there, where left 82, 83 behind. You see the flat line there, middle part of January towards the end of February, and then the big jump with that combination of cold storms, heavy moisture, a lot of local moisture, and really piled on the snowpack down there in the Southern Sierra, which are also our highest mountains. So don't forget that. But you see also while we went past 82, 83, we melted out faster. So that said, we had as friendly a melt season as one could have with such an extreme snowpack, able to manage it without really significant impacts beyond planning to manage the growth of the Tulare Lake, and did that with a lot of teamwork, and I'll talk about that in a minute. For those of you wondering what it looks like, there is a managed Tulare Lake bed as the snowmelt comes in, and the blue there on the right side of the image is the snowpack. You can see a couple of the reservoirs, and then you can see from the dark, which is the water, where the rivers were flowing, putting water into the lake bed region, which the farming communities there manage with cells to try and keep water to as few acres as possible. But you can see kind of a footprint of where the whole lake bed is, and it is still there. A friend just sent me a photo today of what somebody flying over it saw, and it's a lot of this space in here that is still underwater. And in 1982-83, the lake was there for 2 years. So definitely some impacts in the agricultural community as those fields are out of service. All right, so how do you manage such an extreme event? Well, you do a lot of collective work, really working with our partners in the Forecast Center for forecasts, working with the response community at the State Operations Center. And Andrea mentioned while we were getting ready for this, the really good fortune we had of having our partners with Regional Weather Service helping inform the State Operations Center, and my time there with the State Operations Center to really talk about how we make use of the forecast and some of the observations. Now, we're very fortunate here in California. We're standing up a new observing program for snow that is based on aerial remote sensing that uses airborne LIDAR and mass spectrometry to get albedo and depth of snow, and then do some modeling to really have a good sense of how much snow is where on the watersheds. We use that information that helped really guide the melt forecasts that really enabled reservoir operations to manage these flows in a way that really tried to maximize benefit, minimize hazard, and then the water that ends up in the downstream areas be able to manage that and really maximize our ability to try and put as much of that into a depleted groundwater system as we could. Get the best benefit out of this year that we took a lot of coordination, a lot of communication, and really appreciate the Weather Service's help in that regard. So let's talk about measuring snow. Bulletin 120 is the state's report for our snow water. Based on multilinear regression, snow, precip, and runoff, 3 variables. And there in pictures, you see the head of our program, Sean, out at Phillips Meadow, which is where we do our media snow survey with a snow sampler. Technology developed in the 1930s, still in play today. We see up at the snow lab, we've got some equipment doing a lot of experimental work with them, which then are pushed into indices that you see there that go into the regression equations. So what are we doing now? Well, we start with, we've been given $10.25 million from the state budget to develop this more advanced snow measurement program. We have a lot of partners with NCAR, M3 Works, and the Airborne Snow Observatories Incorporated. Working in those watersheds that you see there, we use the Model I snowball to actually model the snowpack and the state of the snowpack, including cold content, how ready it is to melt, and then use that to feed into WRF Hydro to model runoff. These are the watersheds where the models are up and calibrated, where we're working with the others. The map there you see is where we do the Bulletin 120 forecasts, and the ones that are kind of faded underneath, those are where we're not doing flights yet because we don't have a full budget for this. This is an expensive program, but it provides just unparalleled data in terms of how much water and how much snow is on the landscape, which is really helpful, particularly in extreme years like this. So there's the team and just some of the products that they put out, which really lets us see how much snow is in where and at what elevation, which is really helpful because then you can communicate when it warms up, where is the melt going to happen? Really helps combat that notion that, oh my gosh, it warmed up, everything's going to melt all at once. No, it's not. The snow actually has to work through some phase changes before it can actually be ready to melt. So great program, great teamwork. Really like working with these folks. And this comes from a research effort out of NASA's Jet Propulsion Laboratory to prove the Airborne Snow Observatory observing technology. So happy to have been a participant in that research program and now pivoting it into a program. So how expected was this year? Well, here is from October 7th with the alert work group presentation that I made. Happy to say, hey, the potential for the wet extremes late December through January, gave them a heads up a few months ahead of time. Pretty excited about that saw the potential for that. But the rest of it was complete garbage. Really didn't anticipate those second and third sets of storms, the extremes to the extent they were. It's one thing to say it's wet. It's another thing to say you're going to deal with kind of boundary level conditions that haven't seen in a generation. And from 70% versus the over 200, complete bust there. So a lot more work to do in that seasonal outlook work. So finish up here because I know I've probably run long. Boy, this was a year with multiple forms of extremes. We pivoted really hard from really dry to really wet and had to manage one of the largest snowpacks in the observed records. Understand now that as we head into El Nino, really trying to understand what's the potential for novel extremes. In this case, really looking potentially more coastal. And how to manage those novel extremes, not coming from dry to wet, but starting from a really wet condition. So the antecedent conditions this year will be very different than they have been for a lot of the past decade.
Megan Thiemann is from the Bureau of Reclamation. She is a civil engineer for special projects in the Bureau of Rec Interior Region 8, which is the Lower Colorado Basin's Boulder Canyon Operations Office. She has a bachelor's and master's degree in environmental engineering from the University of Florida, and she holds a professional engineer's license in the state of Nevada and is a certified project management professional. In the Reclamation's Boulder Canyon Operations Office, she assists the office chief on the coordination of office program goals, projects, and supports the office in matters associated with the Colorado River drought and reservoir conditions. Megan's presentation will provide an overview of the Colorado River Basin, and it's one of the most critical sources of water in the West. Lots of agriculture depends on this river system. So she'll discuss the hydrology, the operations and projections, and review the impacts from the snow season that we had out here in the West. So Megan, take it away.
Okay, yeah, thank you, Andrea. And before I start going, just want to double check that my screen is showing.
Yes, you are looking good there, yes.
Okay, great, thanks. All right, so before I get into hydrology, I typically like to provide an overview of the Colorado River Basin. And really, as Andrea mentioned, the Colorado River flows through some of the hottest and driest parts of the country, and its water is vitally important. So on this slide here, you can see the hydrologic boundaries of the Colorado River Basin. As shown, the basin is divided into two, an upper basin and a lower basin, and operations are governed by the law of the river, which is a compilation of numerous compacts, federal laws, court decisions and decrees, contracts, and regulatory guidelines. In the basin, there's 16.5 million acre feet of water allocated annually, 7.5 million acre feet to both the upper and lower basin, and 1.5 million acre feet to Mexico. Inflows into the system are highly variable from year to year, however, so we have quite a bit of storage. In total, it's about 60 million acre feet of storage capacity, which is about 4 times the average inflow volume. We also generate quite a bit of hydropower in the basin, which helps power millions of homes across the western states. The 2 biggest generating facilities are Glen Canyon Dam, which forms Lake Powell in the upper basin, and Hoover Dam, which forms Lake Mead in the lower basin. Agriculture is the dominant use of Colorado River water, accounting for about 70% of total use in the United States. And then 40% of water is exported outside of the basin for areas such as Albuquerque and Santa Fe, New Mexico, Denver and Colorado Front Range cities, Salt Lake City, Utah, and Los Angeles and San Diego in California. And these areas are shown by the red hatching on the map in this slide. And it's just important to note that once that water is exported outside the basin, it generally doesn't make its way back in. And then, of course, due to the high demand on the Colorado River system, all Colorado River water released from the dams is diverted, and the river no longer makes it to the ocean, aside from a pulse flow event in 2014, where we intentionally released the water to make it to the delta and the ocean. All right, so the Colorado River Basin has been in a 23-year drought, and the period from 2000 to 2022 is one of the driest on record. We're also just coming out of 3 back-to-back well below average inflow years from 2020 to 2022. Now we have had pretty good hydrology this year. We got well above average snowpack in the 2022 to 2023 winter, and that's led to above average runoff, which has brought reservoir elevations up a bit. But that said, the 2 largest reservoirs on the system, being Lake Powell and Lake Mead, are still near historically low water levels. So Lake Powell is currently at an elevation of 3,579 feet, which is just 39% of capacity. This is about 44 feet higher than it was this time last year, though. And then Lake Mead is at an elevation of 1,062 feet, which is just 33% of capacity. That's about 20 feet higher than it was at this time last year, but it's still 160 feet below the high water line, which you can see when you look at pictures of Lake Mead showing that white band, or it's sometimes called the bathtub ring, and it was shown in the, it's a little hard to see here, but that's what the cover image showed too. So now this slide here illustrates that above average hydrology. We've seen this water year 2023, which for us the water year starts in October. So it ran from October 2022 and will end this September. Now the graphs show the snow water equivalent for both the upper Colorado River Basin on the left and the Salt Verde River Basin, which is in the Colorado River Basin in Arizona, on the right. The blue line on the graphs represent the snow water equivalent for the current water year 2023, with the red line representing 2022 and the black line representing the 1991 to 2020 median. So looking at these graphs, you can see that we had that well above average snowpack this past winter in the upper Colorado River Basin, where a majority of the inflow into the Colorado River originates. The snow water equivalent peaked on April 7th at 161% of average. And then in the Salt Verde River Basin in Arizona, the snow water equivalent peaked on March 3rd at 246% of average. And then I'll just note that these averages are based on the 30-year period from 1991 to 2020. Now we're also seeing above average precipitation in the basin, with precipitation currently at 116% of average in the upper Colorado River Basin and 134% of average in the Salt Verde River Basin. So next up, we'll look at how that above average snowpack translates into the Lake Powell inflows and how it compares to historical inflows. So this slide here shows the water year unregulated inflow into Lake Powell since it began filling in 1964. The large bar graph shows the inflow in chronological order, while the small graph in the top right shows the smallest to greatest inflow volumes and what years they occurred. Now this light green bar here shows the water year 2023 projected runoff. Then the red, darker green, and dark blue bars show the projected range for 2024 Lake Powell inflow, though that's still highly variable at this time, as you can see. And then this horizontal dashed line here shows the average water year inflow from 1991 to 2020. So as mentioned in the last slide, we had above average precipitation and snowpack in the upper Colorado River Basin. And here we can see that that's led to those above average inflows for water year 2023. And really that's projected to come in at 143% of average. All right. So having all of that above average inflow this year is really great, and it's definitely helped keep the reservoirs from reaching critical elevations in the short term. But as you can see here in this slide, we have had years of above average inflows during this drought already, particularly in 2011, where the inflows were even a little greater than what we've seen this past year. Yet the reservoirs have stayed on that overall downward trend. And then just one more key point I want to point out from this larger graph is that historically, despite this really high variability that you see in inflows into Lake Powell, we didn't see many consecutive extremely dry years in which the unregulated inflow was below 7 million acre feet, shown by this orange line, until the drought started in 2000. So only once before the drought, after Lake Powell filled, did we see that happen, and that was 1989 to 1990. However, since the drought started in 2000, we've seen that happen 3 times, from 2000 to 2004, again in 2012 to 2013, and then more recently from 2020 to 2022. So this just illustrates that long-term drying trend, or that drying trend that we're seeing in the basin since the drought started. So this chart shows the total Colorado River system storage going back to 1960. The blue section here represents Lake Mead storage. The gray section represents Lake Powell storage. So then this top line here would represent the combined Powell and Mead storage. So looking at this graph, we see that the system was close to full in the early 1980s and again in the late 1990s, just before the drought started. However, again, when that drought started in 2000, we had 5 back-to-back years of below average inflows, and system storage declined to around 50%. It managed to stay around there, although we did have an overall decrease until 2000. And you can see where we had those small increases due to years with that above average hydrology. But then in 2020, we had those 3 back-to-back years of below average inflows, which caused the system storage to steeply decline once again. And then now with the good hydrology from the 2022 to 2023 snow season, we're projecting the combined Powell and Mead storage to end the water year at 35% of capacity. So you can see that in the graph here, how that good hydrology has brought the reservoir storage capacity up. But I'll just note that that combined capacity, when you look back, it's still around where we were at when Lake Powell was first coming online and started filling. So it's still pretty historically low water levels. And now moving on from historical trends, I'll go over our 2-year projections. So the slide here shows projections from our Colorado River midterm modeling system, which we refer to as CRIMS, for Lake Powell. The blue line represents the probable maximum scenario from our 24-month study. The green line represents the most probable scenario from our 24-month study. And then the red line shows the probable minimum scenario from the 24-month study. The gray lines represent our probabilistic projections, which are 30 years of past hydrology run through current operations. So the main thing I want to mention here is that last fall, these projections were much lower than the projections you see on the slide and showed increased chance of Lake Powell dropping below the minimum power pool this year. And again, minimum power pool, that's the point at which Glen Canyon Dam would no longer be able to produce hydropower. But with this above average hydrology for water year 2023, the projections have improved and no longer show any traces at Lake Powell going below minimum power pool. That's shown by this dashed line here on this slide, in 2024 or 2025. Now I'll also point out here that you can see the historical Lake Powell elevation from December 2022 to June 2023. So you can actually see where Lake Powell's elevation started rising once all of that snowpack started melting. Now this slide shows the CRIMS projections for Lake Mead. So similar to the previous slide, the blue line here shows the probable maximum scenario. The green line shows the most probable scenario. The red line shows the probable minimum scenario. And the gray lines show the probabilistic projections representing 30 years of past hydrology run through current operations. So these projections are also much higher than what we're seeing last fall due to the now above average inflows. We're currently operating in a level 2 shortage condition, and last fall we were showing increased chances of having to operate in a level 3 shortage condition next year. As of July, it's looking more like a level 1 shortage condition, but of course we haven't made any determinations yet. Next year's operating condition will be determined really in the next few weeks by our August 24-month study. Then I'll also point out from the historical data here from December 2022 to June 2023, where we see Lake Mead's elevation increasing, again, due to the higher inflows as a result of the good hydrology. And this is just interesting because typically we'll see Lake Mead's elevation decrease as we move from spring into summer, since that's the high water use season. Now, that said, a lot of these projections still show the lower Colorado River Basin remaining in shortage conditions in the next few years. So this line here at elevation 1075 is what triggers a level 1 shortage condition. So while these increased flows from the 2022 to 2023 snow season have helped, the reservoirs are still low, and we need to continue planning for drought and long-term aridification in the basin. That's what I have for the presentation. I did put our website up here on this slide. We post a lot of data on there. So if you're interested, feel free to check that out. That's also where we post our 24-month studies. And then I'm happy to answer questions if we have time today, but if not, my email's on the slide there, and feel free to reach out anytime.
Okay, I'm still not seeing too many questions. Check one more thing.
Hey, Jenna, I have a question for
Sure.
Dave. This might be
Sure, go ahead.
one Mike might have an interest in answering too. So a lot of areas, particularly in the Southwest, have actually, in the newer normals, have become wetter in October. And have you seen any correlation in an uptick with snow in those months, just because of the fact that it's gotten wetter as well? Because, you know, Dave, you were showing a lot about how melt-off has occurred earlier in the spring, but what about with the fall and early season winter climatology for snow in the Intermountain West and out west?
Well, I haven't looked in great detail in the Intermountain West, but in a general sense, we are seeing more October and November snow cover over North American continents, primarily up at the higher latitudes, middle high latitudes in the center of continents. So not necessarily in the Southwest, but I would assume at higher elevations, it might be cold enough already to get some snow in those areas, but primarily the signal for more abundant fall snow cover. Again, it's been in the high latitudes of North America and over in Siberia. Really interesting how that's happening. We think it could be tied in with some atmospheric flow patterns that are bringing the cold in there. And we know there's always been the cold, but they're bringing the moisture in too, either from the south or off a more wide open Arctic Ocean. So there's a lot of research needing to be done there. But again, as far as Southwest US, I'm really not sure.
So at least for California, what we're seeing is really either years where we get a decaying tropical system, either a decaying typhoon that gets cut into a jet and brought over fairly quickly, or decaying Eastern Pacific storms that are tending to provide our September-October precip, setting the stage for the new water year. Need to do more work to see how that works, and certainly how it interacts again with the High Sierra. Our highest mountains are at the southern end of the chain, so really kind of an interesting topographic setup.
Okay, any other questions? I'm still not seeing any in the chat box. Any other questions from our other panelists though?
Well, since Dave got into maybe some causes or reasoning for the changes in the snowfall, have you guys, any one of the speakers, have you guys had any thoughts or conversations on the climate system of, you know, what was really driving this unusual winter of, like Dave said, the haves and the have-nots? Any thoughts on that you've heard in the research community on reasons?
Not yet from me. Still a lot of diagnostics to go back and do and unpack. I think in the case, you know, where one I suggested that a potential decaying timing of La Nina might open that door. That's largely based on that time window as our climatological peak in atmospheric river activity. So if you weaken that high pressure, there are other forces that can break through. And in this case, it was a rather vigorous jet that had stood up. But the structure and formation of that jet to be there when that broke down happened, don't have yet. And really don't have then the second set of circulation dynamics, which was still La Nina-ish, but located further west, allowing the cold sliders to come in and interact with the moisture plumes, leading to some really anomalous snow.
Yeah, it was clearly, at least east of the Rockies, a classic La Nina pattern, with the storm track up through the Great Lakes, bringing the warm precipitation up into the mid-Atlantic and parts of the Northeast. Of course, further north, up in northern Maine, they were somewhat above normal with snowfall, but that's despite the fact they were warm, they were still cold enough to snow. As you went further south, it just wasn't cold enough to get much snow. So that was a pattern east of the Rockies, kind of a classic Ohio Valley storm track with a mild, not necessarily dry east, but a snow-free east.
Yeah, and out west, I think what you saw was, again, we had a flattening of the ridge, really strong jet for that 3-week window, but the rest of winter was very much a La Nina with a high pressure. But a really deep digging on the east side there in late February, where it dug down almost to the Mexican border and then did that trajectory strong kind of through Four Corners and up into the upper Great Plains. So kind of some interesting signatures to dig through and then figure out the nuances that we think drove it.
Yeah. And then back east, you can look at even a North Atlantic oscillation, and you couldn't buy a negative NAO until we got into late April. It was too late for snow most places at that time, although the mountains of West Virginia got some good snow the first week of May, their biggest snows of the season in some cases. But it was up at high elevations at best at that point. So you just couldn't buy a negative NAO, and a positive NAO, you're just not going to get a lot of snow in the east.
Yeah, and I think that does come down to then the timing of the evolution of these features relative to kind of the geophysical seasonal timing.
Right.
Okay, guys, thank you so much. Andrea, Chris, did you have any parting thoughts before I kind of wrap it up and we close it up?
No, just other than thank you so much for great recaps from all three of you. We really appreciate your time. We will see what we can post as far as slides. Dave's may be a little hard because some of his slides will be going into an article, so we'll have to see, but we'll be in touch on what we can post and share with you all aside from the recording. So thank you again to our three wonderful speakers.
Thank you.
Yep, and I just wanted to offer that I think I'm sharing my screen right now of where we post those recordings. And then also next month we'll be doing a couple of webinars, so be on the lookout for our announcements. At the beginning of the month, we'll be doing an ENSO communications webinar with some ENSO blog experts. And then at the end of the month, we'll be doing Winter Outlook IDSS Showcase with our NWS field offices. So keep a lookout for the announcement for those. And again, thank you to all three of our speakers today. We really appreciate it, and we appreciate your time and great presentations. And thank you all, and we will see you on the next one. Have a good day, everybody.
Thanks,
Bye.
everybody.
Bye.